Screencast, I'm going to analyze from calculus point of view the problem of freely falling object. Uh, if we see the picture, so it depicts that with every uh, increase in time, the distance covered by the object increases. For example, in the first second, the object covers a distance of 5 meters. In the next 1 second, it covers a distance of 15 meters. And in the next 1 second, it covers a distance of 25 meters. This problem is simple. We can calculate the distance value covered by the object at every time given. We have the analytical expression for that. It is half gt squared. And we can also compute the velocity value at every time, at any time. It is 9.8 times t. Uh, and we can also calculate the velocity as it hits the ground and the time to reach from height of 100 meters to the ground position. So the objective is to analyze this problem from calculus point of view, which means the analyzing the characteristics of changes, like we have seen that well, it is something which is claimed by the textbook of Thomas calculus. So let's analyze it in with the help of calculations in Microsoft Excel sheet. So here is the Excel sheet. I can select the time values of my choice. Therefore, this is the independent variable of the problem. So I have got several values. The distance covered is half gt squared. So 4.9 times t value and square of it. So this is consistent. Okay. And then the displacement value, as it was already at some height. So when s was 0, so h was maximum. So they are complement to each other. So h will be equal to 100 minus the value of distance. So at time t equal to 0, the ball was at height 100 meters. And with time, its height is going to decrease. And somewhere before 5 seconds, it is going to hit the ground. So that's the mark where we have to proceed. Let me first plot the space-time diagram of this freely falling object. So I insert a graph of points. So it requires data to be selected. Here is the option to select the data. So add a series, and this is for displacement or height. So abscissa values, these are the time values, and the displacement values are to be plotted on vertical axis. So we have got the scattered plot of the free fall problem. I move this chart to a new one. So it is chart 2. Some options to improve the view, and paint the same one on the vertical axis. Then the markers, color options for marker and line. So marker options, increase the size so that they are easily visible. And for the reference of axis, the chart options, I add axis titles, primary horizontal, this is time, in seconds, and the primary vertical axis should be the height h of t in meters. The size, okay, the size format has been painted on the axis titles. Now we have these scattered points. The simplest thing, the approximation, is to join these points with the straight lines. So let's see how they appear if they are joined with the straight lines. I have to look for the option in the plots. So xy scatter and join these points with the straight lines so that uh, every segment is distinct. For the line, I use the different color and improve its visibility by increasing the width of the line. So we have got 1, 2, 3, 4, 5 distinct segments. And for each segment, we can calculate the rate of change, which is the average velocity. So let's do these calculations. So slope. So the slope requires 2 points. So for the first segment, the slope will be the ordinate value, change in the ordinate value per unit change in the abscissa value. So this is the slope for the first segment from 0 to 1, and this is the average velocity, and the similar calculation will yield the slopes for the other segments, like minus 14.7 is for the segment defined between 1 to 2. So these are the slope values. The slopes are constant for first degree polynomials or the linear model. Uh, However, in this case, we have 4.90 t squared, or in this model, this is the second degree polynomial. So in order to describe a second degree polynomial, it is clearly uh, apparent here that the slope is not solely adequate. So now we can I can compute the second order slope, which is slope of slope, and it is equivalent to, in this problem, it is equivalent to the average acceleration. So this requires the um, ordinate to be considered as the slope and abscissa as the time. So this will be computed as the ordinate change divided by the change in abscissa. And this is very interesting. This minus 9.8, as the object was falling, therefore it is minus 9.8. And which is interestingly equal to the gravitational constant. So the second order slope is constant for a second degree model, second degree polynomial. So let's compute here the velocity defined at every point. So velocity, exact velocity, which is available at every time because we have the analytical expression for that one. So it is 0 minus 9.8 times the time value, and we can compute on that for the time values of our interest. Virtually it is available, it can be computed for any time value. Now let's make a comparison between the velocity, exact velocity, and the average velocity which is available from the slope. Of course, they must not be equal. Uh, they can be reasonably uh, close to each other uh, if the time is contracted, time is considered very, very small. So then the slope value can lead to the velocity value, and which is the approximation of slope of a secant line to the slope of tangent line, which is the very fundamental approximation used in the derivative definition. Uh, now let's plot the slope and the velocity value. So I choose the graph of points, scatter plot. Again, it requires the data to be selected. So add a series. I have exact velocity, abscissa values to be selected from the time. We change the position of this one first. Okay. Then select the data, add a series, velocity, x values, the time values, and y values to be selected from the exact velocity calculation. Now, time values first for x, coordinate of the point, and the ordinates we selected from velocity. So the first set of points have been generated, and then another series for the slope of slope, which is equivalent to average velocity. So x values are the time values, and y values to be selected from slopes, and that's it. And the velocity in the expression of analytical expression, it is a equation of straight line. So it is logical to join these points with the straight lines. So I can change the uh, point type of scatter plot to the connected points. And with this, we find a very nice result that the two lines are parallel, and the parallel lines share the same slope value, which is apparent in the average acceleration calculation. So they share the same slope value. They are parallel lines, and the slope of for velocity expression is 9.8. This is the analytical one. And numerically, with these slopes, we have found the average acceleration to be minus 9.8. So it is a very nice observation that for a second degree polynomial model, we have the slope of slope, which is the second order slope is constant. For linear model, we have first order slope constant, and for second order model, we have the second order slope a constant value. And likewise, we can consider that these for third degree polynomial model, we will expect, and there will be the third order slope will be constant parameter for that process. So this is all that I had to discuss. I had to discuss for this demonstration.